Experience with fans of a certain type used in an aircraft engine has suggested that the exponential distribution provides a good model for the time until failure. Suppose that the mean time until failure is 25,000 hours. What is the probability that a randomly selected fan will last at least 20,000 hours? Okay, so let's say we have a random variable x, and that measures time until failure of this particular fan used in aircraft. Okay, and we see that the mean time until failure is 25,000 hours. That suggests that lambda is one failure per 25,000 hours. Okay, one failure per 25,000 hours. What's the probability that a randomly selected fan will last at least 20,000 hours? Okay, at least 20,000 hours implies 20,000 or greater. Okay, at least 20,000 is more than 20,000. 20,000 and more, however, the probability of exactly 20,000 is 0. So we could think of this either way, greater than or equal to 20,000. This area right here is the probability that x is at least 20,000. Okay? So what's this probability? That is 1 minus the cumulative probability, this area right here, evaluated at 20,000 hours. Okay? That is 1 minus e to the minus 1 over 25,000 times 20,000. Okay? So that's just arithmetic, very straightforward to do. That probability would be 0.4493. Okay? The probability that, given this average time between failure, the probability that a particular fan will last more than 20,000 hours, 0.4493. Now let's look at most 30,000 hours. At most 30,000 hours. That would suggest less than 30,000 hours, or less than or equal to 30,000 hours. Again, same difference. Okay, let's take a look at what that looks like graphically. Here's x, here's our distribution, here's 30,000, and this is the area that we're wanting to calculate, less than 30,000. Okay, that is the cumulative distribution evaluated between 0 and 30,000. Okay, that's the capital F of 30,000, which is 1 minus e to the minus 1 over 25,000 times 30,000. Okay? And if we do that, we should get 0.6988. Okay? So roughly 70% of our engines are going to last at most 30,000 hours. What's the probability of between 20 and 30,000 hours? Okay? What's the probability that, that should have been random variable x. What's the probability that x is between 20,000 hours and 30,000 hours? Okay? Well, that is this area here. Here's 30, and here's 20. Okay? That area right here gives us the probability that x is between 20,000 and 30,000 hours. Okay? That would be capital F of 30,000 minus capital F of 20,000. Okay? This cumulative probability here minus this cumulative probability here gives us what's left over. Okay? So we can work this out. This is 1 minus e to the minus 1 over 25,000 times 30,000, which we found over here. And from that, we're going to subtract off 1 minus e to the minus 1 over 25,000 times 20,000. And if we do that, we should get 0.6988 minus 0.5507. That probability is 0.1481. Okay, this probability right here, 0.1481. 0.1481. So what's the probability that a randomly chosen motor, or a fan, excuse me, what's the probability that a randomly chosen fan will last between 20,000 and 30,000 hours? 0.1481.